Everyone left for the holiday already? Feels like, for the most part. Okay. As a reminder, you do not have class on Tuesday, and then obviously not on Thursday either with the holiday. So what I want to try to do today is get through most of what I have planned on spatial cognition, so that when we return to the holiday, when we return from the holiday, will be, that's where my mind is. When we get back, we can wrap up on this and talk about the last topic, which will be numerical cognition, before a final review and getting to the end of the class material. Okay. So we were talking about spatial cognition when we left off last time. We were just starting to, and I did the demonstration where I asked you all to point northwest, and I don't know who was right or who was wrong. I didn't actually assess it, but I know that there wasn't a lot of agreement, meaning that in general, most don't know where northwest is, right? But you were better at identifying Peavine parking lot. Now, I used Peavine parking lot because both are aligned, right? Peavine parking lot is northwest, and yet you could recruit it. You could recruit that location when I gave you the specific building, but not when I gave you the cardinal direction. What I'm doing in this case is highlighting two types of location information. So a big part of spatial cognition when we're talking about navigation is just knowing where things are. This is the problem you're solving when you're navigating. Getting to a particular location, knowing where that location is so you can tell other people about it, right? But it's about marking a position in space. The marking the position in space can be done in different ways, right? So these are what we describe as different frames of reference. One type of reference frame, a very well-known type of reference frame, is known as the egocentric frame. And it's just like it sounds. When we brought up this idea relative to Piaget's theory, this is about you, yourself, and in this case, using yourself as a marker for the location, right? So the self is the reference frame. The self is what tells you where something is located, right? So to my left, behind me, some distance away, ahead of me, right? In each of those cases, I'm using the self as the reference point to indicate where something is located. Okay, make sense? These are some of the examples as I already mentioned. Okay, what's the challenge with saying something like, if you ask me, you know, where's your clicker? Can tell me where your clicker is so I can go get it? And I say it's on my left over there. What's the challenge with telling you or giving that information to you about location from the egocentric point of view? Yeah.
Like especially if you're like facing each other.
Yeah.
It's like if it's your left, then it's my right, and it gets confusing.
Your ego is not my ego,
Yeah.
right? So you have to adjust for that. That's a problem. Anything else? Okay, so I just told you, you can go get my clicker to the left, right? And now I'm talking to you over here, and you're like, oh, let me go get her clicker. It's no longer on my left, right? So it's the problem. So there are a couple of problems with the egocentric point of view. One is that it makes communication with people challenging because there are different egos that are having to be compared and contrasted. The other thing is that the ego doesn't usually sit still. Right? So I move around in space, in which case saying it's to my left only works if I can continually update it. Now, there is a way in which you can encode from the egocentric reference frame and use it if you're updating. Okay? This is actually known as path integration. So oftentimes, you know, when you're trying to go from one place to the other and return, you do something that's basically retracing your steps, right? That's a kind of path integration where you're using the egocentric reference frame and just updating it to make it useful depending on where you are, right? So if I go from point A to point B, right, in this direction, then I can just, that's easy, I just go back to A, retracing my steps. It doesn't have to be this simple, it can be more complicated. We can often, go from A to B, then to C, and to get back to A, you may just retrace your steps, right? So that's one way in which you can rely on the egocentric point of view to maintain your location and other locations in space. It's taxing, right? Taxing meaning that if you're going from here to here and retracing your steps, right? Any little, you have to keep all of that information in mind constantly. Any little error along the way also displaces you in a way that can become a big difference if you continue making the little errors along the way. Okay, but there's another way in which you could use a sort of egocentric frame of reference that's a bit more sophisticated, right? That suggests that it may not just be the egocentric frame of reference, or it could, but it's more sophisticated than just retracing your steps. So if you're going from A to B to C and then you want to get back home, let's say A is home, you can retrace your steps. What's the other way to get back to A that I haven't drawn here?
From C to A.
Right? When you do that, that's really impressive. It's still an egocentric frame of reference that you were using, but it allowed you to extrapolate a more direct path. This is something that non-human animals do a lot of, and they do very well. Ants can do this kind of thing up to like distances of 30 miles, right? It's amazing, and just sort of retrace your steps directly back to the A, or extrapolate the positioning back from C to A without having to retrace your steps exactly in the previous path. Okay. When people start to do this in their minds, and if you start to have a representation like this of the locations in your head, where you could go from A to B to C, and then you can immediately go back to A, this in the literature is often referred to as a cognitive map. Okay? This is telling you, right, that people and animals can represent this space in a way that's fairly veridical to what's out there in the world, and it allows for making inferences about locations that may exist in between and whatnot, right? If you didn't have a map in your head, you couldn't go directly from C to A, right? You can do it because you represented these three positions spatially laid out this way. Okay, does that make sense? Okay, so this is, I think it's sophisticated when you're starting to extrapolate other paths, but it's a very basic type of cognitive map because it's relying a lot on the ego and where the ego is going in space. But of course, when the ego is walking around in space, we're also seeing other things out there that are potentially helpful for us in terms of our location representations and these maps that we're forming. So this is where we start to talk about the allocentric frame of reference. So when I asked you guys where Northwest was, that was a type of allocentric frame of reference, right? Because Northwest has nothing to do with where you are in space. Regardless of where you are in space, there's a Northwest that remains fixed, right? And that's a really great way to get around the world. Now, of course, you're all terrible at it, right? Because you know where Northwest was. But if you can use it reliably, it is highly reliable, right? Because no matter where you are, Northwest will tell you where things are in the world, right? Okay. That's one type of allocentric source of information. The other type, and what's important here, is that the frame of reference now, in contrast to the self, is the external world. So now we don't care about where the individual person is. We care where things are in the world. That can tell us where we might be and where the locations are, right? So we can start putting markers out here in the world, right, that tell us where locations A and B are that are less dependent on where we are in space, right? I'm just sort of marking different, the different positions here with what I would call landmarks, right? So that's the other thing you can kind of build into your cognitive map now in your mental representations, in addition to where you're walking, where things are out in the world that can tell you where you would be relative to those things if you were to place yourself in that space. Okay. When I said, where's Peavine, and you all pointed at it, Peavine was being used as a landmark, right? So you're pretty good at identifying an important landmark in our environment. So you were in that case using an allocentric type of information, not ego, right? I'm fairly confident that if you were another building and I asked you to point to Peavine, you could probably do it again, right? So it's not dependent on where you are. In fact, you would adjust where you point to, depending on where you are. So that was a landmark that you were able to use and use well. Yeah?
So when you say landmarks in an individual, it's like other people? I don't understand, like, what is individual?
Oh, sorry. When I say what's a landmark and what qualifies as a landmark, I just said that Peavine with parking garage was being used as a landmark. Do you think this would be a good landmark? Meet me over by my bubbly can. Bubbly can, I mean, I don't know. It might be here one day, it might be in my office the next, it might be in the trash the next, right? So that's just meant to say that landmarks and the landmarks we use tend to be these individual stable objects. So where your car is parked, probably not a good landmark, right? Because it moves around the world. The Eiffel Tower, better landmark, right? Because it's a stable thing out there in the environment. So that's just meant to describe what typically counts as a landmark and what we use as landmarks. So Peavine parking deck is a stable, large object that I can ask you about that you can use to determine where you're going to park your car, where you might meet something. So it's a type of landmark. Usually, though, when we use landmarks, we also represent a kind of information known as distance, right? So oftentimes, the landmark is not the Eiffel Tower or Peavine. Sorry, the landmark is the Eiffel Tower or Peavine, but where the desired location is not the landmark itself, right? So it might be the restaurant 2 streets down from the Eiffel Tower, right? Or, you know, the house, however far away from Peavine, right? So when I say meet me at Peavine, I'm using a landmark to describe the location, but in this case, the landmark and location are one and the same, okay? There are other times where the location is some distance away from the landmark, so that means that not only do you, or a child who's representing the location, not only do you have to encode the landmark, you have to encode the distance away from that landmark in some way, right? So maybe the B positioning here relative to the landmark, right, is actually some distance and direction away from it, and that's how you're doing it, okay? So these are the kinds of information you can use that is available out there in the world to be able to represent locations, to be able to navigate, to get to and from places. Okay, the last type of allocentric information that I mentioned before is based on direction. Direction does seem to be hard for a lot of us. In this case, we can use things like cardinal direction, north, south, east, and west. You can also use sense in some cases as directional information left and right, but here the problem is it's a type of direction that is tied to the egocentric frame of reference, so it can be it can be confusing, but usable, at least in some cases. Okay, So those are the kinds of information we can use when we're navigating out there in the world. So far, so good? Any questions? Okay. So when you want to test how able we are to use these different kinds of information, you can set up interesting experiments that require humans, adults, or children, or even non-human animals to find some position in space, or to get to some position in space. Okay, here are where a lot of the research begins on navigation and location, not in humans, in non-human animals. And then a lot of the human experiments get adapted from these animal experiments. This is my first experiment ever as an undergraduate, as a zoology major, testing rats in a pool to see where they can navigate towards. This is a rat in a small swimming pool. Putting rats in a swimming pool to see how they navigate is amazing. It's great for two reasons. One is rats are great swimmers, so I don't have to worry about them. They'll be fine. And the second thing is they hate water, so they're going to work really hard to get out of the pool, right? Meaning they're going to try to use information in their surrounding environment to figure out where's the platform that I can get onto to get out of this water, right? Okay, so this is known as the Morris water maze. It's not represented exactly correctly here. So this is just a training trial where the water is clear and you can actually still see the platform in the water. Typically the way the experiment is done is it's a milky substance. You just put a milky substance in the water so you can't actually see the platform from the water. To find the platform, you would properly have to use this thing on top of it, this cone, or other information that's in the surrounding room, okay? So again, you put the rat in the pool, the rat can't see the platform, and then you ask, what information out there in the environment is it going to use to get to the platform? Here's a really easy kind of landmark. This is your kind of P-vine landmark, because you're telling the rat to kind of get to P-vine, right? It doesn't need to know anything about how far away the platform is from the cone. The platform is the cone, right? The platform is the landmark. When you use this kind of landmark that doesn't require additional distance or direction information, it's known as a beacon. Okay, so in the literature, this is known as a beacon, and it's a pretty easy landmark for animals and even children to use. Yeah?
I'm confused. So you just put the mouse in the pool,
Mm-hmm.
and they have to get to point A, basically. That's it.
That's it. You make it sound so easy.
No, because
No, I'm kidding. Well, it
looking
doesn't.
like that,
It
like,
doesn't
they
know
can,
it.
They can see it, right?
Yeah.
So like,
It
they just
is-
have to swim.
That's right. Right. So if you understand that this thing, and it's trivial in some sense, which even young children can do, right? If you understand that cone is where the platform the platform is, then yeah, you swim right towards it. I could have made this harder, right? I could have had the cone projecting out of the pool, no little platform for it to stand on, and then he'd have to figure out that it's some distance away, right? So he'd basically go to the cone and then turn and go some distance away to find the platform. That's a way to do a landmark that isn't a beacon. Make sense?
Yeah.
So, and of course, it helps you find something, because at that point, the rat is not going to be swimming on this side of the pool, right? Because he knows that the platform would be some distance away from the beacon. But yeah, this is super easy. All he has to do is know the beacon marks this, X marks the spot, basically. And then he swims towards it, and it's great because, like I said, you can measure how easy these beacons are for the rat by looking at how quickly they get there, right? The easier it is, the more quickly they get there. Like I said, they can swim well, but they don't want to be in the water, so they zoom right towards it, no matter where you place the rat, and it gets on top of the platform. Is that clear? This is something that even young children can do. But again, it may seem sort of trivial, except that you do have to recognize a correspondence between this object in the world and the location that it marks, right? That they actually do go hand in hand. Okay. I already indicated how you could make the task a little bit harder with in the Morse water maze by taking the beacon and moving it some distance away, making it a landmark that you use with some distance away from the platform. So you could either do it in the Morse water maze, or you can do it in this maze called the radial arm maze that people also use with rats and now humans and children. The logic is similar. What you do in this case, though, is you place the rat in the center, and then one of these arms that they can walk into is baited with some treat they like. So now instead of making it kind of aversive so that they have to get out of this space, they're actually just excited and looking for the treat, right? So now they're also motivated to look for the treat and to get there as soon as possible. The way you could do this is that you can ask if they use landmarks at some distance. And the way it was done in this experiment is you have a surrounding room, and then you have different things placed on the walls that are serving as landmarks to see whether the rat can figure out when they're in the center. They look around the room, and if the arm that's baited is closer to some target over here, some other landmark at this distance, then they should be able to go there right away. They should be able to use the landmark in the surrounding environment, where it is, how far it is, to get to the arm that's baited, okay? So you've made this a little bit harder by using landmarks that are some distance away in the context of the radial arm maze. But suppose I wanted to make it easier. I wanted to mark one of these locations with a beacon instead of a landmark some distance away. What would I do? Any thoughts? How do you indicate location here more similar to what I did here? Any thoughts? Suppose I gave you a flag, little flag. Where would you put it? Exactly where the tree is, right? So you could put a flag just here and mark it directly, right? That would be the easy way to do it. So you can do these different paradigms and test to what extent kids and animals know about different kinds of landmarks by doing these kinds of manipulations, okay? So it's pretty straightforward. And across different experiments, non-human animals like rats and young children find this condition with a beacon much easier than they do the landmarks that are not immediately adjacent to the target location. In the literature, what people have described is the fact that cue learning is a lot easier than place learning, okay? Place learning seems to be more dependent on development of the hippocampus. That is a relatively slow development than cue learning, which can be based on regions that are implicated in object recognition, that involve discriminating objects and now marking location. This type of learning is earlier to develop, both in terms of the neural mechanisms and in how you use the information for determining location. But that's the distinction here, is cue learning based on the beacon and place learning based on these landmarks that are some distance away. Making sense so far? Okay. A big part of getting around the world, like I already said, is using allocentric information that involves distance. I've already said that when the landmarks are some distance away, it's harder to use. But that doesn't tell us when kids start to become sensitive to certain information like distance, right? And how sensitive they are. So one paradigm that has been used with young kids is a type of sandbox paradigm. Kids love playing in a sandbox to build things, make things, and you can use a sandbox to hide things that kids might really like to see whether they can find it when it's hidden. So in an experiment like this, you place the kid in front of the sandbox, you take a toy they really like, you stick it in the sandbox, it gets buried, and then you smooth it over. The sandbox is great because once you smooth it over, you can't tell where it is, right? The only way to find it is if you had registered some information about the distance of the object from the wall, for example, right? Now, if a kid doesn't know anything about distance, they're not able to represent distance, or maybe they don't care. All they care about is their toy and finding it. They're probably just going to start searching randomly, right? They're just going to start digging through the sandbox and not using any principled way to find it. By the way, this is a lot like what squirrels do. So people think squirrels are great at representing location because they bury all their nuts and then they eat and they're fine, right? People are like, oh, this is great. Look at these squirrels. They bury the nuts in the yard and they go and they find their nut. They don't find their nut. They find everyone else's nuts, right? So what squirrels do is because they live in these communal environments and they're burying nuts, they're lucky that there's a lot of them being hidden, and so they can find whichever ones. They're usually not finding their own, right? So they're actually not doing what you would want them to do, which is to represent the location of that specific object, right? And I don't know more than that when it comes to squirrel spatial cognition. Maybe it's, again, adaptive. It's fine if you live in a communal environment to not care about the location. Maybe they just can't do it. I don't know. But they're not using distance information or any kind of location to find their food. Okay, but can a kid use distance information to find their toy? So, some details here. This is work that people did with kids starting at about 16 months of age. It's a pretty young age to start, in part because there wasn't good reason to think that young children would represent distance of objects in a surrounding environment, right? So now we're talking about an allocentric frame of reference that they might be using. Yeah?
What does it mean children move laterally?
Yeah. So this is the way the experiment is set up. You give kids, you test 16 to 24-month-olds. They're in front of the sandbox. You say, hey, here's your toy. I'm gonna play hide and seek with you. I want you to find it. You hide it. You smooth it over. You don't let the kid reach for it right away, right? Now you turn the kid around and let's say you move them to the end of the sandbox, to one side, another side. You move them somewhere around the length of the sandbox. In other words, wherever they're standing originally, looking at where you're hiding the toy, is not where they end up, or not where they are when then you let them search for it. The reason you move that is because if they see it, and you're hiding it, they don't move, you smooth it over, they can just kind of reach for it where they had been previously reaching for it, right? Remember the kid in the A not B error? You don't need to know a lot about where it is initially if you're just looking and reaching for it. So they move the kid to see whether, one, the question is, are they going to be totally egocentric? Meaning that when I said my clicker's to my left, right, if the object was here and they represented it as to my left, and now you move them here, are they just going to go to my left again? Because they're using their bodies and their arm movements as where things are in space, right? That very egocentric perspective that Piaget talked about. Or are they going to adjust, their arm movements, depending on where they're moved to, right, to find it. So the idea here was, if kids can do distance, if they're representing distance, and they care and they understand location, then they're not going to search randomly. And they should be able to succeed if you move them laterally along the box. And that's what they found. They found that as early as 16 months, when you move them laterally around the box, a long box, the box is actually, in real life, it looks more narrow than it does here. Here it looks wider, I don't know why, but it was kind of a long, narrow box, around 5 feet long. And kids could find the object pretty accurately even after they had moved, within about 5 inches, which again is pretty accurate given the long space and that these are only 60-month-olds. So they're not just going around the world thinking, okay, you know, toy, 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 and just searching for it randomly, or toy that's always, you know, in my pocket on the left side of my body, or, you know, in this position. They are presumably sensitive to these locations and using things like distance to find it, right, to represent the location. Does that make sense? This is especially interesting because with younger babies, I mentioned some of this when we were talking about things like ventral and dorsal early on. If you show a baby that's younger than this in a habituation-dishabituation paradigm, if you show them a cool toy they like, and you hide it in the sandbox, right, and another object comes out of there, it's like they don't necessarily know what's going on, right? If they care about the location, they don't seem to distinguish between the objects. Sometimes they don't care about the location and only care about what the object is. So it doesn't seem to be like this nice integrated information about a target object and the locations all in one. Here you're showing that at minimum, they care about the object because they're searching for it and they know where to go based on this distance information. Okay, but one question you could ask is when the kid searches correctly and has been moved laterally along the sandbox, are they really using what we're calling this allocentric information, which is that they see the rectangular sandbox and they're thinking some distance away from the boundary, for example? Or could they be using something else like the path integration we talked about before, which is more egocentric, where you kind of just retrace your steps and you go back and search for the object in that other location, right? So it's really hard to figure out whether these young children are using that type of allocentric, more place learning type of deal, or whether they're relying on the egocentric kind of information that doesn't really care about the relations among the things in the environment. It's more about where I am and retracing my steps and sort of tracking it in that way, okay? One isn't necessarily more sophisticated than the other, but they're different kinds of maps and representations, which is why people were trying to figure out exactly how kids were representing this information in their minds and brains, right? Are they using, like I said, the egocentric frame and updating where they're going in space, or are they taking themselves out of it and really representing the world around them and thinking, okay, that object in relation to the side of the sandbox and some distance away? It's very different kinds of information, and it's not clear that they'd be able to use both types or one over the other. Okay. So enter a type of paradigm that has really dominated a lot of the literature on early spatial cognition and the development of early spatial cognition. It's known as the disorientation paradigm because what it leverages is the fact that when you lose track, when you are stopped updating or tracing your steps, there's no egocentric frame of reference left, right? You're completely disoriented. Think about coming out from underground of a subway and looking around the world. How did you get there, right? What direction did you take? How far away was it? You have no clue, right? You're totally disoriented. How do you figure out where you are? By looking around the world and seeing, okay, what's the name of the street? Where's the landmark that I recognize, right? It's not about how did I move underground from point A to point B. No, you've lost track of your movements. So you're totally disoriented and you're forced to use the external environment to figure out where the locations are, right? So that's sort of the brilliance of using this kind of paradigm to say, how are we navigating in the world, and can we use allocentric information, the external world, to represent locations? Do human adults do it? Do young children do it? Do non-human animals? Okay, so here's a paradigm that was originally done with rats again, and then it was modified for young children, which I'll show you. Okay, but here's how it works. So, and this is a very strong test of that allocentric frame of reference, because it's asking whether you encode the surrounding environment. Okay, so you take a rat and you place them in a chamber like this. It's shaped like a rectangle. And in this space, there's some coverage on the ground, okay? And the coverage is important because what you do is you bait one of the corners with food for the rat. So the rat is in the chamber. He sees you reach in there and bait one of the corners. So now it's hidden underneath this coverage in the ground. It's kind of like the sandbox again. Rat sees it. Rat's in this rectangular environment. Now you take the rat out of the rectangular chamber, put him in a separate cage. He's outside of the chamber. You twirl him around, you move him around the experimental environment. Poor little thing doesn't know where it's going, right? You bring it back. Put it back in the rectangular chamber, right? So this is my little disorientation. Bring him back. Where does he go search? Okay, here he is, back in this chamber. Where do you think he goes? Where would you go? Thoughts? Yeah.
Towards the food.
How come?
Because because the rat saw the experimenter, put it in that corner, so it would probably,
You think it's based on sight? Where he saw it?
yeah, I guess.
So, and do you think it matters where he's placed in the environment?
It might be also on smell.
Okay. If it's smell, he's gonna go there too. They have a good sense of smell. Okay. Any other thoughts? Might he go anywhere else? If he's using smell, he should go right to the target, right? What if he's not using smell? What if he's using the shape of the surrounding environment, the rectangle? If he's using the shape of the surrounding rectangle, he has to go either there or somewhere else.
Or a different
That's right. If you are using the shape of the surrounding environment, when you get placed in this rectangle, there are two corners that are identical, right? This one is the corner that has the short wall to the left of the long wall. When you turn around, short wall to the left of the long wall, right? So if you get placed in this rectangular environment and you can use the surrounding shape, that's where you go. Okay? That's what the rats did. Now, you might be wondering again, why, if they smell the food, why didn't they just go to the food, right? Hold on to that. They didn't do that. Yeah.
Wait, so you're saying they went to the corner without the food?
They went to both.
Oh, okay.
Equally. And so, for example, and you'll see this with children, if you do this 4 times with the rat, you're going to get like 50-50 searching, right? Half the time they might go here and half the time they would go there, right? If they were not using the rectangle, if you put them in there, and usually when you put them back in, you'll have them face this wall or that wall or this or the other wall, right? And in that case, if they're just going to the corner they saw before, they're just going to search randomly, right? They'll go to each corner equally. Out of 4 trials, they would go to each. That's 25% of the time across. If they're using the rectangle, though, they should go to this one 50% of the time and this one 50% of the time, right? So they're spending their searches at those 2 corners. If they were using only smell, they would go there 100% of the time. Are those 3 possibilities clear? Question?
How did the experimenter control for the smell then?
The experimenter didn't control for the smell, at least in the first bit.
rat go to like the other corner if
Yeah.
they realize, like, so for example, they went to the bottom right first and they realized the food wasn't there, did they go to like the top?
I don't want to answer that just yet.
Okay.
My answer is I'm not telling you, not just yet. But what's important here is that in this first experiment, they've done experiments where they control for the smell, meaning that you hide the food and then you take it out and there's like no smell there, right? Or you use something without an odor. It's pretty easy to control. But what's important here, and I'll reinforce it again in just a bit, is that even when the smell is available to the rats, and rats do use odor to get around the world, in this experiment, they were searching most of the time at the what I'll call the correct corner where the object was hidden, and the one that's diagonally opposite, which in this case is known as the geometric equivalent. Based on the geometry of the surrounding space, they're identical, okay? So now they do another experiment. So here it suggests that they're using this geometric allocentric information to locate the food. Okay. Now, for some reason, they weren't using the odor, but you could still try to distinguish these two corners. You can distinguish these two corners in another way if you add some additional information. So here's the follow-up. So now, the rat is tested in the rectangular corner again, container again. And this time you add a different colored wall. I have the wall here as blue. Rats are basically colorblind, so what they actually did was luminance, so you'd have like one really bright wall compared to a dark walls. But that's how you do it. Okay, so now I add this landmark to the rectangular chamber. And if you're using allocentric information, which we think the rats are using based on what they did before, right? The odor was available, they didn't use it, and instead they used the shape of the environment. So they seem to like allocentric information in this reorientation paradigm. So if they like allocentric information, and now you add the blue wall, where should the rat go? I already told you. So the rat doesn't use the blue wall, right? And here, if you can integrate the geometry with the different colored wall, the landmark, you should have just gone to the correct hiding corner, right? You should only go to the direct hiding corner because now both of them have the short wall to the left of the long wall, but one of them has a short blue wall, not the other one doesn't, right? So now, if you can integrate both kinds of allocentric information, you should just go to the correct corner. The rats don't do that. So again, they keep searching at the correct corner and the one that's diagonally opposite. Make sense so far? So, before we interpret what this all means, let's first ask, what if you tested kids? What would they look like? So on the one hand, they might be sort of oblivious, right? Because the shape of the surrounding environment is a rectangle. It's kind of complicated, right? You've got short walls and long walls and these left-right relations. Maybe they can't do it at all. So maybe you do a version of this with kids and you indicate one corner as the hiding corner, as the target corner, and they just search randomly, right? They just go to each corner equally because they don't even know how to use the geometry, right? That's one possibility. Another possibility is that they look more like the rats and they can use the rectangular information, right? And then you can also test them when you add the blue wall as well, or a different colored wall. Okay. So when I show you the data for this experiment, I'm actually going to show you the data for 18 to 24-month-olds, teeny children, right, that are just starting to walk around the world, toddlers still. This example I'm going to show you here was with a slightly older kid. This is a 3-year-old. And so the 3-year-old is going to be able to do the experiment largely on his own. The way it works is you bring kids into a rectangular room. In this case, it's not a full room. It looks more like a playpen, and the surrounding space is circular, right? So that you can't use any other information in the environment. So the kid is placed in this rectangular box. And each corner has a little hiding spot. And when you start the experiment, you start it like you did with the rats. The experimenter shows the kid that, oh, look, there's this cute object, this toy, that is hidden here, for example. The kid sees it, just like the kid saw, just like the rat saw the food being buried in one of the corners. After the kid sees it, you disorient the kid. So remember, with the rats, we took them out of the chamber, put them in a cage, twisted them around the room and so on, and brought them back. With 18-month-olds, when you do this experiment, typically what we do is we ask the parent who's there also to pick the kid up, cover their eyes, and just like spin around a bunch of times, right? I love that experiment. I did this experiment as a grad student. You see a really interesting gender difference between moms and dads when they come in to do the experiment with their kid. You tell the parent, okay, pick up little Johnny now, cover his eyes and spin around a few times, right? Moms are very gentle, spinning around, and they put the kid down. Even a little spinning makes the kid a little dizzy, right? And dads come in, and it's like, and then the kid gets it, he's like, falls on the floor, you're like picking up the kid, you okay, are you nauseous? Too much, right? Even when you tell them, gentle, not gentle. So that was always fun to watch. But the key thing is then, after the kid is disoriented, you place the kid down in front of one of the walls and you say, where's the toy? And the kid searches for it. So this is a slightly older kid. This is a 3-year-old who's going to disorient himself. When they get to be a little older, you just tell them to cover their eyes. Sometimes you put a little eye mask on and you say, okay, circle to the left, now turn to the right. You do it enough times to make sure they can no longer remember where they're facing, and then you ask them to find the toy. So here's an example with the 3-year-old. It's sped up a little bit so the audio sounds weird, otherwise it goes really slow. But so the kid sees the object being hidden. He already knows what he's supposed to do. He's done this a few times. She's going to put a mask on him. She's going to tell him to rotate around, right? And he does this a few times. When he looks out into the world, he's going to have no idea which corner is baited with the toy, right? You're totally disoriented, and then the environment looks completely symmetric. So now she takes the mask off of him and she says, go look for it. This is a case where she probably should be standing out of the way a bit, but that's fine. So where does he go? Okay, so this is a kid who is 3 and is, they get several trials of, look, she can't even find her way out. They get several trials of this, because it's perfectly symmetrical. They get several trials of this, and you look to see where does the kid search, right? So that kid was 3, went to the corner that was diagonally opposite, the one I've been calling the geometric equivalent, wasn't there, and then immediately turned around and went back to the correct one. That geometry is in the kid's head, okay? The environment is, we're asking, now that you can't track where you are in space anymore, right? And you're disoriented, can you look around the world and use the information that's around you to figure out the location, the allocentric information? The answer is, here's a 3-year-old, absolutely. Okay, the 3-year-old goes to the opposite, either most of the time goes to the correct corner or the diagonally opposite one, and when he goes to the diagonally opposite one and he's wrong, he sometimes even turns around and goes immediately to the other one. Okay. These are data now from 18-month-olds. These are the toddlers. Okay, so what I'm showing you here is in one experiment. This experiment was originally done by Liz Spelke and her former graduate student. It was a Hermer and Spelke experiment. This is the proportion of time that kids go to each corner. Okay, if the object is hidden here, what you're seeing is that at approximately 40% of the time, they go here and here. Together, that's 80% of the time, way above chance, which would be 50%. If you were guessing, and you were not using the rectangle, it would be 25% at each corner, and then you would add these up and they'd be about 50, it would be 50%. So the fact that it's way above 50 shows that they are using the rectangle to go to these two corners, okay? So this was really cool when it was first done in the late 90s. These are 18-month-olds who no one thought, right, were really keeping track of where they were going in space, let alone what the environment in the surrounding world was telling them about where they are in space. This was a really big deal. Even with people using habituation paradigms, violation of expectations, saying that babies know more than what Piaget thought they did. These are 18-month-olds who are barely walking, right, and now able to kind of reorient themselves in a space to find the right location. Okay, so this was a big deal on its own. So what they did was, they did this experiment. They said, look, 18-month-olds are as good as rats at using the geometry of a surrounding environment, and it's kind of cool because rats are pretty good at navigating. They use lots of different things to navigate. So this was pretty amazing. So then they asked, what about if you add a different colored wall like we did with the rats? Are they going to be even better than the rats? Remember, the rats didn't use the different colored wall. The rats would go to the two corners based on the geometry. Well, the kids look just like the rats. So in this original study, this was experiment 2 of the study, this was the average proportion of time that they went to the two geometric corners. And on average, again, this is still around 80%, right? Which is significantly above chance. But it's not, they're not going here to the correct corner. Now, at this point, you might be wondering, is this just how this works? Does everybody look like this? So let me clarify. By the time you get to be an adult, they tested undergraduates in these experiments like you, and in this case, you go here. You went here around like 98% of the time. I don't know why it wasn't perfect. Maybe someone was like sleep deprived or whatever, right? But in general, by the time you get to be a human adult, you do go to this corner. But in young children and in non-human animals, these rats, you're only using the geometry. Yeah.
But we get it right 100, like pretty much all the time with the landmark? Or
Yeah.
even without the landmark?
Without the landmark, you go to these two corners, like probably even higher than 80%, closer to 100%, right? And it's great because, like, even when I asked you guys, when I was putting up the image of the rat in the rectangular box, and I'm like, where would you go? There's kind of I'm not sure, like, how would I know, right? What's the information here? People aren't very good at reporting that they use the geometry, but they do, right? Because they end up going to these, and oftentimes, and this original experiment was done with Harvard undergraduates, not dummies, right? And they would ask them, how did you solve the task? I don't know, I just went to where the keys were hidden, right? But how? I don't know, I knew. There was something about the lighting maybe, not the lighting, can't be the lighting, right? It had to have been the geometry. So people have a hard time articulating how they're doing this navigation, but based on the fact that they're going here almost 100% of the time, we know that they're using the geometry. Okay, so the Harvard undergraduates look like the kids and the rats. They go to the two geometrically equivalent corners when there's no landmark. When there's a landmark, they go to the correct corner. But before that, before adulthood, right, the young kids and the non-human animals don't go to the correct corner because they seem to be favoring the geometry, the shape of the space over this landmark. Yeah.
For the adults trial, was it with the
It's, it's both, right? Because it's without the blue wall so that they go to these two, and with the blue wall they only go to this one. And I should say that it doesn't matter where the blue wall is, meaning that if the object isn't right next to the blue wall, let's say it's hidden here instead, they'll go to this one 100% of the time, right? Really showing you that they're integrating both kinds of information in this way to get to the correct corner. They're not just going, well, we know they're not just thinking it's right next to the blue wall. They're not just using it as a beacon, because if they were using it just as a beacon, they would go to these two the most. But they don't. They only go to that one. And again, it doesn't matter whether the blue wall is right next to the object or somewhere else. But what's important is that when you have a blue wall, in addition to the landmark, you now have enough information to distinguish between the two geometrically equivalent corners. So it shows that you're using both types of information. So even though the kids, like the rats, are using allocentric information, which again we think is pretty sophisticated because it's out there in the world, you don't have to be paying attention to it, and yet you are, and you're using it to figure out where you are in space. It's pretty remarkable, but it seems to be specific to the geometry and not the other kinds of allocentric information. Okay, so what do they tell us, these studies? Just to summarize, they're showing us again that even young children are capable of using allocentric information. And in this case, the allocentric information is the geometry, right? They're also telling us that, like the rats, kids are using the geometry, the rectangle, exclusively. They're using it at the expense of the other allocentric information that's there, the blue wall. So kids and rats can use allocentric information, but they prioritize certain kinds of information over others. In this case, they prioritize the geometry, the rectangular space, over the landmark. They use it exclusively. So, some people have called this a type of modularity. The idea that you have a representation in your mind and brain that is encoding the geometry of the space to be used for navigation, but it can only do that, right? It's hyper-specialized for that and nothing else. And no matter what other kind of information you give the kid or the rat, they're going to use the geometry. Now remember that whenever we say modular, what we're saying is that the system that is modular doesn't process anything else. It's encapsulated, right? So to remind you, this modularity is like when we talked about the Mueller-Lyer illusion, right? Remember that this was an example of how the visual system and visual perception is modular, right? It's modular because even though you tell the person, even though you tell visual perception that this line is exactly the same as this line, it can't see it that way, right? The knowledge does not penetrate visual perception. The visual system does not make use of it. So here we have the idea that our brains have a cognitive module for processing geometry, which processes geometry and doesn't make use of other kinds of allocentric information like the different colored wall. Is that making sense? Go, tell me.
Like, they're just looking at the geometry, like that's the only thing they're taking into consideration. They're not taking into consideration like the cues at just when they're younger.
That's right. So we're talking about a geometric module right now in rats and in kids. And we're saying that our minds and brains, right, for human and non-human animals right here, have evolved a system, a cognitive system for processing geometry in the surrounding environment when we're navigating. That's what it's specialized for. It's useful, but limited because it doesn't take in other information that might be useful. these are the data which suggest, right, that there is this cognitive module. So one thing I want us to consider now is, why would that be? So I'm showing you data consistent with a cognitive module for geometry. Given some of the limitations, why would we have evolved such a system for navigating, for reorienting, right? Or reorienting in particular, right? Rats, as I showed you on the Morse water maze and the radial arm maze, they could use landmarks. They can use landmarks. But when you're disoriented and you're having to, again, figure out where you are in space for the first time, there's this hyper specialization for using geometry and geometry alone. Why would the geometry be specialized in this way, encapsulated in this way, more than processing landmarks, right? Any thoughts? Think about the world in which we evolved. Think about looking out in the world, I don't know, seeing mountain ranges, right, out there in the world, the shape, the structure that it forms, versus, yeah?
I think like color changes a lot, like the seasons and stuff, so
Yeah.
it's like better to know like
Yep,
geometry
yep,
than
Yeah.
like
Yeah.
I guess overall shapes.
yeah. So think about the landmarks in that world, right? They're not the Eiffel Tower, right? They're not Peavine. They're probably things like a big tree, which for the most part is good. It's usually there, it's usually stable, but it changes color, right? With the seasons, it may actually die off and cease to exist in that environment. So one possibility is that the reason we would have evolved a system for prioritizing geometry when we're reorienting in a world that we're navigating through is geometry is highly stable, right? In the real world, the geometry is like the shape that the mountain ranges make, for example, right? It's not, what's not stable are the landmarks in the world in which we would have evolved, because those can change with respect to color, with respect to whether they survive the seasons and so on. So that's one idea, that geometry is this more stable thing that we would have evolved to pay attention to, even at the expense of these other things that might be in the environment, because they're not particularly stable. And I already said, at the beginning of the class, that stability is key for things like landmarks. Okay. these guys? Why would language matter? So this individual here is a member of the Kuuk-Thaayorre tribe in Australia, located here. If I ask this gentleman to close his eyes and point northwest, not a problem. And in fact, everyone in this community could do the point northwest. Remember, I said you guys couldn't do it. I think at the start of the course I mentioned that I've done this demonstration in other institutions. It doesn't matter. No one can do it. Americans cannot do it, right? We are not good, Americans, North Americans, right? We're not good at tracking cardinal direction. These guys are amazing at it. And I think I mentioned when you left, a 5-year-old among the Kuuk-Thaayorre could answer where northwest is with their eyes covered. How come, right? So maybe going back to some of the other things you guys were saying, maybe it's about exposure and experience. Maybe these guys navigate a lot more, and they do. They navigate a lot, starting very young. They take long trips. They walk, around the country and so on a lot, looking for wildlife. They do farming in different areas. So maybe that's part of it, right? But the biggest part of it is, it turns out, is the language they speak. So the Kuuk-Thaayorre do not say left and right like we do, things on my left or things on my right. They don't say that. They don't really say front and back. If I want to tell you where my remote is, my clicker, I'm going to say it's on the southeast side of this room. I actually don't know if that's the southeast side, don't quote me, because I don't know, like you guys, right? That's how they talk. So they talk, their spatial language is cardinal direction. And it's not just cardinal direction when saying, meet me at the parking lot that is northwest. Their cardinal direction is even for small things, where we say left and right all the time, right? When they reference some bug on their leg, they may say the bug on my northeast leg here or something, right? So their spatial language is cardinal direction. When they say hello to each other, right? When we say, hey, hello, how are you? Their hello, how are you greeting basically translates to hello, where are you headed? We could say where are you headed metaphorically. No. For them it means where are you headed in space? And so your answer has to be, I'm okay, headed north-south. Headed northeast, right? See how bad this is? Headed northeast, right? So literally, their whole day is about cardinal direction language, right? Imagine how good you would get at cardinal direction if I forced you to keep track of it wherever you were going, right? So there's a way in which, this is actually, I actually find these folks and what they can do with cardinal direction amazing. Initially, I've never studied them, but initially when I heard about this group of people, I was like, oh my God, they have these superhuman powers, right? They seem like birds, right? That can fly and navigate using their magnetic sense. But I was like, but it's even cooler than birds, because birds have basically like magnets in their beaks, literal magnets, right? That they can use to track magnetic sense. We don't have that in our brains. So how do we do it, right? So it turns out that we do it by paying attention. Right? If you have to pay attention to where you're going, because your language forces you to pay attention to and talk about it, we can do it. Right? We have the skill for it. But because we don't talk about it and it's not meaningful in our language, we stop keeping track. Right? So this is an example, again, of how language can be really important for something like navigation and spatial cognition. Doesn't seem like it should be, but it is, right? So even these guys can use cardinal direction. And the idea is that it depends on the language, right? So language can have a really important role here in how we represent the spatial world and how we navigate. Yeah.
So if you did the disorientation thing with them, isn't it relative to where they are in space though? Like, do you know what I mean? Like, do they have some instinctual understanding of where north is, or would it have to be relative to
Presumably,
environment?
if you did, I have not done disorientation, so I don't think anyone has, as far as I can tell. I think I would have heard of it. You presumably couldn't disorient them, right? Because they would know that the object is like in its north east corner or something, and they would be able to go to the correct corner the entire time. I don't know if that's true or not. I think it's unlikely because I think the way they're doing cardinal direction is by using landmarks in the environment, right? It's not by a magnetic sense. So, you know, Atlanta's terrible for this, right? But there are cities, like when I lived in Chicago, it is easier to know where north, south, east, and west are, right? You've got a big lake, right, that orients you, and you know where east and west are. Same thing in some other cities. In Toronto, the Lake Ontario is on the south side, on the south side of the city, right? So again, there are landmarks that allow you to drop your cardinal direction onto it, and that's likely how they're doing it, right? So yes, unless they had magnets in their brains and using the Earth's magnetic field, then you know they wouldn't be able to do the reorientation one and just go to the target location. Does that make sense? So language is meaningful, and when we talk next, we can then go back to how is language working in the reorientation